Normalize the wave function psi x is equal to a exponential minus ax square. Capital A and small a are constants over the domain minus infinity to plus infinity. So we have studied the normalization condition, and if n is the normalization constant, then n square within the limit minus infinity to plus infinity psi square dx or d tau will be 1. This is the normalization condition. Here n is the normalization constant. Mod psi square dx means psi star. Here we are considering the equation, that is the wave function psi x is a e raised to minus ax square. So here the equation will be a square, we raise the normalization constant, a square integral within the limit minus infinity to plus infinity psi square dx. We are considering psi square means psi star. Then here psi is a e raised to minus ax. This is ax. Then psi square becomes, that is a square e raised to minus ax square, the whole square, that is a square e raised to minus 2ax square into dx will be 1 according to this condition. That is a square minus within this integration limit, that is exponential minus 2ax square into dx is equal to 1. This is psi star. Psi is this one and multiplying with the psi star. This is a real function, so we are just taking the square. So this will be 1. And we are considering this as e raised to minus. We have a standard integral e raised to minus 2ax square. This will be root of pi by 2a. This is standard integral. Integral e raised to minus 2ax square dx within the limit infinity to plus infinity, it will be root of pi by 2a. So substituting this value, then we get, that is a square into this root of pi by 2a is equal to 1. That is a square into, this will be root of pi by 2a. Pi by 2a will be 1. Or we can calculate the value of a as, or a square is equal to root of 2a by pi. 2a by pi, or 2a by pi the whole raised to 1 by 2. Therefore, a will be, a is equal to 2a by pi the whole raised to 1 by 4. This is the value of a. Hence, the wave function, the normalized wave function with is, that is the psi x is equal to 2a by psi x is equal to a e raised to minus ax square. A is 2a by pi the whole raised to 1 by 4 exponential minus ax square. This is the normalized wave function. And the next question is, that is a particle limited to the x-axis has the wave function psi is equal to ax between x equal to 0 and x equal to 1, and by psi is equal to 0 elsewhere. Find the probability that the particle can be found between x equal to 0.45 and x equal to 0.55. B. Find the expectation value x of the particle's position. And we have studied the equation for the probability density and also expectation value. And the probability density, or first we are considering the probability A. The probability, we are considering it within the interval, this interval. So we can consider the probability as, that is the P is equal to within the interval. This can be taken as x1 and this is x2. x2 probability is psi square dx. We are considering the x-axis only. So probability is equal to integral x1 x2 psi square dx. And here x1 is given and x2 is given. And the function psi is given as psi is equal to ax. Psi is equal to ax. Therefore, this equation becomes integral this x1 x2 psi square is a square x square dx. And substituting x1 and x2, x1 is 0.45 and x2 is 0.55. x1 is 0.45 and x2 is 0.55 into a square. It can be taken outside of the integration. A square into x square dx. It will be a square x square dx is x cube by 3. That is within the limit 0.45, 0.55. And substituting the value a square into 0.55 the whole cube by 3 minus 0.45 the whole cube by 3. And it will give finally a value that is 0.0251 a square. This is the value. So the probability that the particle is between 0.45 and 0.55 is this value. And the second part is find the expectation value x of the particle's position. We have studied the expectation value and many problems related to the expectation value. And here in the B part, the expectation value x can be written as x equal to integral. That is, a particle is limited to the x-axis as the wave function psi is equal to ax between x equal to 0 and x equal to 1. That is, within the limit we are finding the x value. Therefore, 0 to 1. The particle is limited within the limit 0 to 1 along the x-axis. So, 0 to 1 x psi square dx. We have done so many problems with the expectation value. So we know that expectation value, what is expectation value? And x into psi square dx. Here psi is ax. So psi square will be a square x square. Then a square can be taken outside, a square into integral 0 to 1. Then the x into psi square. Then a square x square, that is x cube into dx. Then we get a square into x raised to 4 by 4 within the limit 0 to 1. And we finally get a square by 4. This is the value of the expectation value. The next problem is, this is the problem. That is, find the condition at which the deBroglie wavelength equals the Compton wavelength. Find the condition at which the deBroglie wavelength equals the Compton wavelength. Next question. And we have studied what is Compton wavelength and what is deBroglie wavelength. And the Compton wavelength it was denoted as lambda c. We have studied it as h by m0c, where h is Planck's constant, c is the velocity of light, m0 is the rest mass of the electron. And the Compton wavelength, the lambda c is equal to h by m0c. And we have the deBroglie wavelength. deBroglie wavelength, the lambda is equal to h by mv. And where v is the velocity and m is the mass of the electron. And we are considering the relativistic variation of mass with velocity. That is, m is equal to m0 divided by root of 1 minus v square by c square. Where m0 is the rest mass and v is velocity. And m can be written as m0 divided by root of 1 minus v square by c square. Therefore, the lambda, the deBroglie wavelength lambda is equal to h by we are substituting the value of m relativistically. That is, we are considering the relativistic variation of mass with velocity. Therefore, this m will becomes, that is v into m is m0 by root of 1 minus v square by c square, or it can be written as h into root of, this can be written as c square minus v square by c square. Root of 1 minus v square by c square is equal to root of c square minus v square by c square, or root of c square minus v square by c. So this will go to the numerator. It will become c square minus v square divided by n0 cv. This is the equation. And we are taking the v outside of this equation. Then it becomes h into v into root of c square by v square minus 1 divided by m0 cv. And this v and v will cancel. The remaining term is h by m0 c into root of c square by v square minus 1. That is, lambda is equal to h by m0 c into root of c square minus v square, c square by v square minus 1, where lambda is the deBroglie wavelength and h by m0 c is the Compton wavelength, lambda c. That is, lambda is equal to lambda c root of c square by v square minus 1. That is, lambda and lambda c are related, Compton wavelength and deBroglie wavelength. Then when this becomes equal, when lambda is equal to lambda c, that is when the Compton wavelength and deBroglie wavelength are equal. That is, in this equation, lambda is equal to lambda c means, that is root of c square by v square minus 1 is equal to 1. Is equal to 1. Or we can just rearrange this, we get, that is c square by v square minus 1 is equal to 1. C square minus v square minus 1 is equal to 1. Or we get c square by v square is equal to 2. Or finally we get, that is v is equal to c by root 2. That is, when the velocity will be equal to the c, the velocity of light, divided by root 2, when lambda is equal to lambda c. This is the condition at which the deBroglie wavelength becomes equal to the Compton wavelength.